So the first lab is graphing techniques. Has anybody, you should have had a little bit of introduction to graphing in math class. Is that true? Yeah. Okay, good. So we're only going to focus on one type of graph, that is using the Cartesian coordinate system, which looks something like this. That's a complete, well, that's incomplete, but it's a beginning for a Cartesian system. This is known as the x-axis. This is the y-axis. This is also called the abscissa. I can remember how to spell that thing. Yeah, I thought so. Abscissa, and this is the ordinate. Okay. So far, I'm only talking math. I'm going to make the transition to science in a second. The this is the origin, and any data point that we place on this graph has two values, one x and one y, right? So on this side, all the x values are positive. On this side, all the x values are negative. And similarly, positive values here, negative values here. For the sciences, most of our graphing takes place in this quadrant. There are four quadrants. This positive quadrant. We do, however, sometimes go into this quadrant with data, and occasionally we'll use one of these others, but we're in this class, we're only going to be using this one and this one. Right? So when you draw the graph, you can ignore this part of it down here. Okay. So when we have a data point, what does that data point mean? Well, it says right where is it? A measurement is, hold on a second. I thought it was right here somewhere. Uh, well, shoot. There it is. Any point on that graph represents an experimental measurement. And it means, based upon this information here, it means that the experimenter has introduced into the experiment an independent variable. The experimenter controls what that variable is. For instance, if I say I establish a temperature in a trapped gas of 50 degrees Celsius, then I measure something, its response to that. So I have controlled the x-axis, the independent variable. That's this axis, independent. So I say 50 degrees here, right? The response is whatever the gas does that I'm measuring. Say it's volume. So I measure the volume of a gas when I make the temperature 50 degrees, and it's up here somewhere, right? So over here is something, let's just make something up. Say it's 10 liters. This is the dependent variable. Okay. So the experimenter controls this. The response is this, and this data point right here represents 50, 10. Okay, X, Y. So how would we label this? Well, this axis would be labeled temperature in degrees C. This one would be labeled volume in liters. So we have to label our graph. Otherwise, we don't know what those numbers mean. So we label this one temperature degrees C and this one volume. This identifies what it's measuring. This identifies the units of measure. Okay. So that data point is has X and Y buried in it. Okay, so if we change the temperature again, right? We change the temperature again, say we decrease the temperature, then we might get something out here. Decrease it again here. So what we're seeing is, as we decrease the temperature, the volume of the gas decreases. And say we only make those measurements. Now, when you're plotting these values on a piece of graph paper, you have to decide several things. One is, how do I get the maximum use of that piece of paper? Right? If you have a piece of paper like this, and you draw your axes in here like that, and all your data points are right here, look at all the space you've wasted. Besides that, with the data points that scrunched together, if you want to go in here and say, well, what if the temperature is not one that I chose, but it's like in between in here, then you want to be able to say, all right, what would the volume be if I chose that temperature? Then if they're all scrunched together, there's no way you're going to be able to do that. So you want to spread out and use the entire page, or as much of it as possible. So you try to spread your data out as much as possible on these axes. Then we've already decided which is independent and which is dependent. Then we want to scale it so it uses as much of the space as possible. So you want your maximum value to be out here somewhere, and your maximum here to be up here somewhere, and then in between you spread the rest out. And when you do that, then you have to choose the units here. Like you've got a grid on the paper. Those are the lines that are drawn on the paper. And then you choose your scale units so that you can get the maximum use out of it, right? In this case, the units are chosen for us, degree C and liters. But you can also say, what does 1 liter represent? Well, in this case, 1 liter is probably about right there. So that'd be 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you label those grid marks. And 50 degrees here would be like, let's see, 1, 2, like that. This would be 0. In fact, the origin is always 0, 0. So it'd be 10, 20, 30, 40, 50. And then 60, 70, 80, and you could go on out if you decided to increase the temperature further. But if 50 is the highest one, then you want 50 to be way out here. And if 10 is the largest volume, you want 10 to be way up here. So you use the maximum amount. Also, you want to pick the orientation, because a sheet of paper is going to be either in portrait or landscape. If it's in landscape, then X needs the most room. If it's in portrait, then Y needs the most room. All right? Things to consider. Now, once we've put our data points on this page, then we want to to draw a best fit line. This one looks like it's a straight line. So you get yourself a straight edge, preferably a straight edge that you can see through. The reason for that is, suppose, let's see, suppose I had more than 1 point. Say I had one down here, and I had one up here, and I had one over here. So we see some error involved. If you think that's a straight line, then you want to position your straight edge so that you minimize the deviations of the points from that line. That's a best fit line. So without a straight edge, I'm going to estimate maybe like this, something like that. And that would be your best fit. We call it a curve, best fit curve. So if you do have data that tends to curve, then you draw best fit on the curve. Or it could go the other direction. And that best fit line, we know, if it's a straight line, we know that it will have a slope and a y-intercept, right? Based upon the straight line formula, right? So here's your independent variable. Here's your dependent variable. Here's your y-intercept wherever it crosses the y-axis. And there's your slope. So what do we mean by slope of a line? Slope of a line is rise over run. So if the point is right here, and there's another point right here, then we can calculate what's the distance between this one and that one in the y-axis, and what's the distance between this one and this one in the x-axis, right? Delta y divided by delta x. And if you can see those on the graph, then you can calculate the slope. That's the slope of the line. Now the slope, if it's this way, like that, if it's a direct relationship, in other words, as this one goes up, that one goes up. So from here to here, if this one goes up, that one's going up. That's a positive slope. And the m will have a positive value. If it's the other way, if it goes this way, then as this one gets bigger, that one gets smaller. That's a negative slope. Okay? All right. So we've got the slope of the line. How do you find the y-intercept? Once you've got the slope of the line, then you just pick two values on your graph, preferably ones that are actually touching the line. Plug those numbers in, the x value, the y value, the slope value. Solve for your y-intercept. Or you can actually cross the y-axis and see where it is. Either way. Then you have a formula for that line. And the value of a formula is that you can do what ifs all day long. Say, what if I had chosen this value instead of any of those? Solve it and find out what the volume would be, what the expected volume would be inside, if it's inside those values. Right? That's where we get to the concept of interpolation. If you pick values in here within the measured range that you didn't actually measure, but they're on that line, then you're interpolating. If, however, that's as far as you went here, that's as far as you went there, and you extend that down, extend this up, and you pick some value up here or down here, that's extrapolating. Interpolation is reasonably safe for giving you numbers that you can rely upon. Extrapolation is risky. because you don't know what's happening beyond that last point. It could be going this way, it could be going that way, or this way, or that way. You just don't know. So you have to specify if you're going to publish your work and you extrapolate, you better be pretty sure that you need to do that. Otherwise, the reviewers are going to hammer you and you may not even get your paper published. And while I'm on the topic, if you're publishing a graph, you're trying to convey information to your reader. And as a consequence, your graph needs to be self-sufficient. It needs to stand alone, which means you've got to put all this information in there on the graph so the reader knows what they're looking at. And then also it needs a title. So you're saying this is what this graph represents, right? Sometimes we say the effect of something on something else. So in this case, it'd be the effect on temperature on the volume of a gas. So you need the title, you need to lay out your grid, the units, and what they represent, right? The value, what's the variable, what are the units? Then place your points, draw a best fit curve. And then if you need to, you can always put an explanatory note in the graph. But that graph has to stand alone. If I take that graph out, I ought to be able to say, this is what it means. Right? So if we're missing information that I've given you, then the graph is not complete. Okay. Excuse me. Okay, we plotted data points. We've drawn a best fit curve. Tilting a graph simply means portrait or landscape. Oh no, titling. Excuse me, titling the graph. give it a title. I thought tilting. Tilting the graph is portrait or landscape. Here's the discussion of interpolation versus extrapolation. Calculating the slope. Right, direct proportion means that way, positive slope. Inverse proportion is this way, negative slope. Okay, and there's how you calculate your slope. And when we calculate the slope of a line, we go from left to right on the independent variable, and then we say what happens to the dependent variable. So this one would be, and you always go final minus initial. So if we're going left to right, the final is here minus the initial. Okay, that's the delta y. If it's negative, then final would be down here minus the initial, which is up here. That's why it's negative, because the final is a smaller number than the initial. That makes the whole value negative. Okay, let's see. There's a discussion of inverse proportionality, and they give you a chemical equation here, which you don't need to worry about right now. We're gonna flesh those out later. But it's just to illustrate that. Let's see. Okay, here's a good graph. Pressure versus volume of a gas. So as we increase the pressure on the gas, what happens to the volume? It gets less, right? So we increase the pressure from left to right, and the volume is decreasing. But it doesn't decrease in a linear fashion. It decreases in a curve, right? We're going to talk about that more when we get to gases and the gas laws. This represents a gas law called Boyle's law. And it simply means that as we increase the pressure, the volume gets less, and it's on a curve. This is a special curve. You may have studied this in math class. It's called a hyperbola, right? The hyperbola, and in math class, the hyperbola has another. It would have one up here, and then it would have another one down here, or it would have here or here. They always have a mirror image. We only use the positive image. So this is our hyperbola. The other characteristic that a hyperbola has, besides having a negative slope, at any point on this line, the tangent to that line, everybody know what a tangent is? It's a straight line that touches the curve. Anywhere that straight line touches the curve, and it changes as we go the curve, then the slope of that line is negative. So that's why we say this slope is negative. What we mean is the instantaneous slope of the straight line tangent to the curve at any point is true for this curve. Also is true is this tail here goes on forever and never touches the x-axis. Or it goes on forever this direction and never touches the y-axis. Ever. Never, ever, never. That's the nature of a hyperbola. Okay. In this case, we've reported the data here. So which one does the experimenter control? The pressure. The experimenter controls the pressure, and the response of the gas is the volume. So this is the x-axis data, this is the y-axis data. And those are the numbers that we plot. 0.25, 96.9, 0.5, 48.4. And those values are plotted here on this curve, and we try to draw the best fit curve. Now, how do you do that with a curve if you're doing it by hand? There's a special device. Have you ever heard of the French curve? It's like a ruler, only it's curved. And it has a decreasing radius curve. So it'll look something like this. Right? So this is a big radius here. This is a small radius here. And you can move that curve around and figure a best fit line to draw for those values. And they're usually transparent because you want to have your points equally distributed on either side of the line. Right? You want to minimize the deviation. So that's what we would do for this one if you weren't using a computer program, and it would draw one for you. So what we see in this graph is a transformation, right? The data as collected is pressure versus volume. But what we don't like curves. Scientists don't like curves unless we absolutely have to use them. We prefer straight lines. So what you'll see very often in the sciences is that data will be transformed to create a straight line. And in this case, we've taken the data, and if we take the inverse of volume here and plot pressure versus the inverse of volume on the y-axis, we get a straight line. Let's see. I'm going to erase this so I can talk some more here. I'll show you why that works. And you'll see this again when we get to the gas laws. This is Boyle's law. P times V equals a constant. Pressure times volume equals a constant. Whenever you see two variables in a product equal to a constant, that's an inverse proportion. Here's why. That is constant. If this one goes up, that one has to go down in order to retain the constant value. Okay, so that's why it's an inverse proportion and a negative slope. Well, if we want to convert this into a straight line formula, what if we divide both sides of the curve by volume? So I'm going to take volume over here, volume over here. We can do that. That's kosher in math. Do the same thing to both sides of the equation. You haven't changed it. So now the volumes cancel on this side, and we've got them on that side. This is K over V. Well, I want to use another math trick and split the volume out. So this means that K in the numerator times 1 over V, keeping the V in the denominator. That's allowed. So now we have, this is our Y value, K is our slope, and 1 over V is our X value. Okay, that's our straight line. Oh, by the way, what's the y-intercept? It goes through the origin, right? See there? Goes straight through the origin. So now if we plot x as 1 over v and y as p, like we did here, we get a straight line. And the straight line is that k value. Now, it's not the same slope as this one would be for any one of the tangents. It's a different slope. We're using different units of measure, so it's a different slope. But it is very useful because we can plot a straight line much more effectively, and we can calculate a formula for that straight line also. Now, one other thing you need to notice is we have, what does this axis represent? It's pressure. What are the units of measure? Atmospheres. With this one, the volume was represented here with units of measure of liters. Okay? When we take the inverse of the volume, we also take the inverse of the units. So here, this axis represents 1 over volume, or the inverse of volume, and the units are the inverse of liters. That's why liters to the minus 1. That's the math equivalent of the inverse of a unit. Liters to the minus 1 would be the inverse of liters. Okay? Now, let me let that cat in. Hello. Go ahead. Okay. After saying all of that, this requires a different title, right? Because we've changed the units. We're still working off the same data set, right? Pressure and volume, but we've transformed one of those units so that we can plot it and call it straight line. And notice that the slopes switched. When we took the inverse of volume, now the slope is positive. The other point I want to make is that whoever drew this graph made a glaring error. See these values, 0.25, 0.5, 0.75? Those numbers possess what I call orphaned decimals. When you have a decimal sticking out here by itself, it's orphaned. It needs both parents. That is, it needs a 0 on the left-hand side. Right? If I see that on anywhere, on a graph, on the answer to any question, doesn't matter, I will count it wrong. I know some teachers in the public schools do it that way, but respectfully, they are wrong. You need that 0 to bracket in that decimal point. Okay. So this is another set of data that's got a negative slope. In this case, the curve is not a hyperbola. Notice, because it intersects the y-axis. I'm not going to spend a lot of time on this one. It can be transformed, right? In this case, we transformed it with logarithms, right? We took the log of this y value, and that gave us a straight line. So we're not going to go into that much detail. So you don't have to worry about this one. Let's see. Okay, from now on, this discussions from now on, in fact, including this one as well, are part of this exercise is required. And let's see. This part is required, and it's worth 78 points. This particular exercise is not a formal report. This is an informal report, which means you just do the work and fill in the answers and submit the hard copy. The reason I'm doing that is because I want to give you time to get your lab notebook set up and get the feel for experimenting and doing this stuff before you actually have to write a formal report. So this is going to be, let's see, this is an informal report, and I think the second one is also, yeah. The second one is laboratory techniques, where we actually go in the lab and we just use various techniques to get familiar with them. That's an informal report also. The third experiment is where we start with the formal reports. And I've given you, well, actually, yeah, I did hand them out. I did give you information on writing a formal report. I gave you a sample report that you could work off of, you could imitate. And I gave you the rubric that I'm going to use to grade so you know what I'm looking for. And then we can talk about it more later. But when we go into the lab for the lab techniques, we're going to be working off of a hard copy document. That's in a couple of weeks. So you'll need your lab coat and eye protection. And I would encourage you to study the lab before you go in. And since we're on that topic, I'll say the first line of defense against accidents in the lab is know what you're going to do before you go in. Be familiar with the lab. Don't just cookbook it. Say, walk in there, open the page and say, oh, this is what I'm doing today. Oh boy, let's go have an accident. Know what you're going to do before you walk in. For the informal labs, it's just a matter of reading the lab and asking yourself questions. What would I do in the case of emergencies? Where are the hazards located? In the formal labs, I'm going to require that you set up your notebook with information from the hard copy so that you can take your notebook and do the lab, and the hard copy stays in your purse or in your briefcase. Or you can leave it at home, I don't care. But your lab notebook is what you work from. So you need to set up your lab notebook in such a way that you can do the entire lab from the notebook. So it's up to you how much information you put in there. You want to put in there enough so that you can do the lab, right? As much detail as you need. When I set up my lab notebooks as an employee of the government, I would put in nauseating details because I wanted to be able to come back 6 months later and repeat the experiment if necessary and know exactly what I did to conduct that experiment. If you're very vague, then you may do it the same way and you may not. Okay, so this section is the required section, and we start off by just answering questions, and you can extract those from the introduction to the lab. And then, let's see, answer more questions. Let's see. And then we actually get to the point where we're going to plot data. Here's your data, right? A study was made of the effective temperature on the volume of helium gas. That's a good title. So the effect of is the independent variable. The temperature is what you control as the experimenter. And the effect of on the volume. The volume is the response. The volume is the y-axis. Okay? And this one right here worth 10 points is where you plot the graph. So you need graph paper, right? There's graph paper in the hard copy of Method. If you find that you need some more when you come to class on Thursday, I'll have graph paper with me so I can give you some extra sheets in case you make a mistake and you have to start over again. So you'd plot that one and then you'd answer questions about it. Here, at what volume would the helium sample have a temperature of 5 degrees? Well, look up here at 5. Is there a 5 degrees there? No, there's not. So you plot the graph, you draw your best fit line, and then you go to 5 degrees on the x-axis, follow it over to the y-axis off of that line, and that's the volume. That's what you record right here. Okay? And don't forget your units, right? The question is asking for volume, so what would the units be? Liters, right? Don't leave the liters off, otherwise I have to count points off, and that takes a lot longer to grade. Perfect papers are easy to grade. You just check, 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 check. Papers that have mistakes take a long time to grade because I got to correct your mistakes and tell you where you went wrong, and it's a learning experience. At what temperature would the helium sample have a volume of 4.20? Now we go the other direction. We go up the y-axis to a volume, follow it across to the line, go down to the x-axis. That's your temperature in degrees Celsius. This one actually tells you to calculate the slope of the line. So how do you calculate the slope of the line? You need 2 data points, right? The y values from those 2 data points, subtract them, and put that in the numerator. Then you subtract the 2 data points x values, and put those in the denominator. Calculate the slope. Now, what are the units of the slope? Let's see. We've got sometimes it helps to draw a picture. Okay, if you've got this graph here, and actually you're going to need some negatives, aren't you? Right? You're going to need some negative x's. So we'll extend it out this way. And your best fit line is going to be like that. Probably, right? Isn't it? As we get bigger temperature, we get bigger volume. Yeah, so it's going to be a positive slope. Once you calculate your slope, like you've got 2 points here, and you go like this and this. So this delta, this is delta x, and this is delta y. No, this is delta x. This is delta y. There we go. So it's for the x-axis, it's this one minus that one. For the y-axis, it's this one minus that one. Gives us a positive slope. So once you've calculated the slope, what are the units of measure for the slope? We'll look at it this way. If it's delta y over delta x, and y is volume, and x is degrees C, there's your units. Liters per degree C are the units of your slope. Then calculate the y-intercept. I mentioned that earlier, but I'll tell you again. Once you have the slope, right, you have the slope here, like that, and that's times x, and this is y, and you have your y-intercept, we want to know that value right there. So you can either read it off the graph, or you can calculate it. I would suggest calculating it because you're going to have to report the equation anyway, right? That's part of the answer. Y-intercept and equation. So you calculate the y-intercept. You say, we've got, when you draw your line, hopefully you will have one of these on the line that will fall on the line. So you pick one. Let's say, I don't know, 6.53 would be volume, would be Y, 6.53. And X would be 50, 50 there. And then you have some value here, right? There's your unknown right there. All right. So you multiply these together, you subtract them from both sides. So there would be this one minus this product. That's equal to your y-intercept. You report your y-intercept. And then when you do the line equation, you have two choices. And I don't care which one is which. You could say y equals mx plus b, and you just put the slope value and the y-intercept value there and say y equals something times x plus something. Or you can say, excuse me, volume equals something here times temperature, right? Temperature, plus something there. That's okay too. Okay, here's another graph, and we've drawn one just like this, right? So this one should be easy. Pressure volume relationship of a gas. And it should look like that curve, right? What you want to do is choose your values of we're changing the pressure. That's the experimenter. So that goes the x-axis. Volume is the y-axis. So we want to go on the x-axis up to, say, 4, right? 4, nice round even number. 4 atmospheres on your x-axis. Use the entire stretch. And on the y-axis, we want volume in liters. The volume in liters is going to go from 14 to, say, 100. So that should be okay to go from 0 to 100. You should be able to get that on the y-axis. Now, which one should it be, portrait or landscape? Which one needs the most room? 0 to 100 or 0 to 4? 0 to 4 should be the shortest one. So that means it's portrait, right? And the volume is the Y, so it needs the more room. So you would draw that one as a portrait. Okay, and that's what we're doing right here. Tell me, is this a direct relationship or is it is there a direct relationship? Right? Remember, direct relationship says as x increases, y increases. What did the P times V look like before? As x increases, y decreases. That's an inverse proportion or an inverse relationship. Let's see. Then we got another one here where we want to transform that data and draw a linear graph of it. So we would take the inverse of these values and plot them against each of the x values. Okay? So you're going to have 3 graphs minimum, right? You're going to have volume temperature, you're going to have pressure volume, and you're going to have pressure inverse volume. 3 graphs minimum for the required section. Then there's a bonus section. And if you feel brave, you can get in there and earn some more points. So you have the potential of making more than 100% on this lab. Let's see. I will say this. I think the second, oh, there's your graph paper. There are two graphs in this one. There's a graph and based on this data, and this graph is based on that data. This is a titration curve, and we don't do that one until the second semester. But I'll show you what it's supposed to look like. Oh, let's see. That's my time. Oh, 3:50. Okay, good, good. If we plot, okay, what we're doing is we're adding base, sodium hydroxide, to an acid, and we're measuring the pH. That is a measurement of acidity of the solution. So you really don't have to understand what's going on as long as you know which one's which. So we're adding the sodium hydroxide, which means that's the independent variable. That goes on this axis. This is sodium hydroxide in milliliters. Yes, milliliters. And on this one is the response, or the pH. Okay? The pH doesn't need an explanation. pH is it, just pH. That's one exception to having the axis identified and then the units of measure. That axis identity is the unit of measure. So you just have to say pH. And what we get is acid is a low pH, and we add base, and it gradually starts coming up and then it flattens out. And then it goes to a point, and then it goes to equivalence here, and then it goes out like that. It's a sigmoid curve. Now, this point right here represents the volume at which the pH reaches equivalence. And what that means is the amount of acid exactly equals the amount of base, the amount of sodium hydroxide. That's what that means. Let's see. So if you plot the data, it should look like that. Sigmoid curves are, this is the only one I know of in chemistry. There are probably others, but I've seen them a lot in biology. The sigmoid growth curve of a population of bacteria, of insects, of larger animals, the sigmoid curve. So you start off at this level, and then the food supply, the reproductive rate is kind of slow at first, and then it just goes boom. And the reproductive rate increases the population until they exhaust their food supply and then levels off. And sometimes it crashes on the other side. But the sigmoid curve is, you'll see it lots of places. This other one, this other set of data here, this is what I call a broken curve. So if you figure out which is which, right, you're changing the temperature, right? A study of reaction of hydrochloric acid and ammonia, a student collected the following temperature data. So over time, as you mix them together, you're measuring the time, and the temperature is the response. So temperature is on the y-axis. And this is time. In seconds, I think. No, minutes, excuse me. Okay, so what you get is the as the time increases, and it looks like it increases in 1 minute intervals, half-minute intervals to begin with, and then that changes to 1 minute. And this point right here is when you mix. That's when you mix the two ingredients. So your temperature is doing something like this, then you mix it and it goes up here like that. That's what I call a broken curve. Now, if you need to draw some conclusions between this part of the curve and that part of the curve, and they don't overlap here, like that, they don't overlap. So what you have to do is extrapolate this one, extrapolate that one, and then say, there's the difference in temperature. Okay, that's why I made those bonus, because it's kind of, yes, it's a little beyond first year chemistry. But if you're game, you can answer some of these questions and maybe pick up a few points. But the rest of these are required. Let me see if I've forgotten anything or if you have any questions. Right. There's a lot of introductory material here.